tamaño ya lo
Eso es verdad, porque la salida del año pasado.
Sí, pues esa es la idea, o sea, básicamente me gustaría hacer un poco para tener más tiempo para intentar hablando con tu vida también.
yo que uso una tablet para estar más o menos, pero si la pobre ya está todo sujeto a la misma experiencia.
Porque se va a la aquí va a haber una sala ya.
Yo el tema que tengo ahí al lado y hablamos 8 horas todos los días, básicamente.
¿Una hora a la semana?
Bueno, una hora a la semana hay como creo que no sé, peor. O media hora cada semana.
Y dejarlas ahí, claro, eso lo echo de menos.
Sí, o sea, eso sí, pero me refiero a que es que hay mucho genio por ahí que sí me vale. Que me quejo, y cada vez que me quejo, pero yo vamos a intentar algo así, yo le pongo verdad porque te puedes notar en
Okay, hello, good morning. Welcome back to our EBD seminar series. Today we have an extra seminar this week, and it's my pleasure to present Pablo Lechon. He's a graduate student at the University of Chicago, and he's going to talk about his research in random matrix theory and theoretical stuff, the things that we also like here. The floor is yours.
For having I mean, I invited myself, but you guys made the room for me, so thank you. And yeah, today I want to talk about this project that we have in the preprint in the bioarchive called Robust Coexistence in Competitive Ecological Communities. And this is a project with Srilena and Paulina, who were two postdocs in the lab that now graduated. Jose Capitan, who is in Politecnica in Madrid, and he's in a really integral part of the project, and Stefano. So I want to start by introducing this concept of intraspecific competition, which has been used a lot by ecologists to kind of model this idea that conspecifics will compete more strongly than interspecifics, right? So like if you are two zebras of the same population and you kind of like need more similar resources than if you are a giraffe, so then you're going to compete more with zebras of your own populations than with the giraffes. And this graph here represents like the resource overlap. And so the more overlap, the more competition, right? So this idea has been really central in ecological literature, and even not only in empirical literature, but also in theoretical works. And in theory, we've been using it to model interactions between species. So a very famous model that people use a lot is the generalized Lotka Volterra model, where you have like the abundance. You can have a differential equation here where the abundance of species I is modeled with some growth rate, right, which we're going to set to 1 here, And then the growth rate that could be, if species I is a plant, could be like the interaction with the environment and how it intakes the nutrients, is modeled or modified by the species that live with this plant, right? So in this case, the growth of the plant is modified by the other species, xj, with some strength that is encoded in this matrix of interactions. And here I plot what people do with this model a lot of the times is they just integrate it numerically. So you have a matrix of interactions where you have the interaction with other species in the off diagonal, and in the diagonal you have the interaction with members of the same species. So those would be AII, and the interspecies interactions would be AIJ. And then you can run this differential equation, and in this case, for example, you will run it from different initial conditions, the solid and the dashed lines, and then we end up in different places, right? Because we don't have stability, global stability. And so this concept of intraspecific competition, right, now AII, has been used for analyzing the stability of ecosystems. And people do it in the following. They, for example, the work of Robert May in the 70s was looking at the stability of a system defined with this matrix of interaction, where you have some baseline interactions B, and then you add a diagonal matrix with some strength alpha that is going to model that strength of the intraspecific competition. And the result that he got is that when you pass some threshold, which we're going to call alpha S, the system becomes stable, right? So imagine if you're below alpha S, sorry, this is actually the reverse. If you're below alpha S, you have different stable states depending on the initial conditions of your system. And if you have your alpha from here crosses this threshold, then starting the system at different conditions will result in the same endpoint, right? You see that the lines over there converge, and the only difference here is that the diagonal of this matrix has increased. So we have more intraspecific competition. And this is a very old result. But another thing that one can look at is the feasibility, right? So it's like, rather than looking at the existence of an equilibrium, we look at rather than looking at the stability of the equilibrium, we look at the existence of that equilibrium. And for that, we need to postulate some model. So we're going to use the Lotka-Volterra model. And the equilibrium of this differential equation, the equilibrium points are those where the derivative doesn't change anymore. So we can obtain them by equating this thing to 0. But this thing can be 0 for two reasons. Because either one of the species is 0, species I is 0, or because this inside the parentheses is 0. So because we focus on coexistence equilibrium, where all the species are present, we're just going to look at this quantity here being 0, right? So if you put this model in matrix form, then you can obtain the equilibrium by inverting the matrix. X star is the inverse of A times the growth rates, which are 1. And if that equilibrium is all positive, then you have an equilibrium that is biologically attainable because all the things are positive, and you cannot have like minus 1 zebra. So, and we call that feasible equilibrium, and that's why we call feasibility. And so the combination of feasibility and stability is very informative of the dynamics of your model. And in this figure on the right, I have 4 examples of the different combinations of feasible and stable. And you can see that if you have both feasible and stable equilibrium, that is, there exists a configuration where all the species are positive, and that configuration is globally stable. That is, it will be reached from different points of the space, no matter where you started. If you have a feasible equilibrium, but this equilibrium is unstable, what could happen, for example, is these oscillations, where because you have an attractor in the, you have a point in the center. Can I draw a little thing there? We don't have markers, no? It's fine. I can do it with my hands. I have imagined that some feasible equilibrium that exists, but this feasible is not attracting, is unstable. So then what could happen if my boundaries where one species goes extinct are repellers, is that I oscillate around this unstable point, but I never go extinct because my boundaries are repellers. So this is just another example. that wouldn't happen if I had a stable equilibrium. And then this one, for example, is where I have an unfeasible equilibrium that is stable. In this place, because I don't have a configuration where all species are positive, some species will go extinct, but which go extinct don't depend on initial conditions. So as you can see here, always the red and the blue go extinct. Sorry, the orange and the blue go extinct, independent of where I start. And finally, unfeasible, unstable, where some species will go extinct because you don't have a feasible equilibrium, but which ones go extinct depend on where you start the system. So this, so this is just to say that the combination of feasibility and stability is going to be informative of what type of dynamics we should expect. So in the competitive Lotka-Volterra model, you can actually observe any type of dynamics, right? But let's start with one species. For one species, the only type of dynamics you can observe is stable equilibrium when you are competitive. When you increase the number to 2, you can see alternative stable states. So you can see unstable equilibria. When you have N3, you can see limit cycles, which is something that you cannot see when you have 2 species. And when you have 4, you can see chaos, which is something that you cannot see with n equals 1, n equals 2, or n equals 3. So right, this says that beyond 4, any dynamics are possible. And here in this talk, I want to ask the question of what dynamics should we expect of models with pairwise interactions that are mostly competitive, and when the models are large and random. And the spoiler is that you can only expect stable equilibrium, right? This is kind of the punchline of what I'm gonna show today, where species coexist stably, independent of initial conditions. So to start looking at, to start getting to that result, let's talk about like feasibility of these systems as for general systems, right? For now, we're not imposing some random ensemble on the matrix A, but we're just looking at if I have some matrix of interactions A, which is defined by alpha and the baseline interactions B, what happens when I increase my intraspecific competition to the equilibrium of my system? So I have my alpha, then I plug it here, I invert the matrix, and I compute this equilibrium, and then I'm going to plot it on the y-axis, right? And this says y star, but this is actually they're very equivalent quantities, so you can think of it as x star. And what happens is, a lot of things can happen, right? It seems very complex in the sense that you can have divergences here, right? For some values of alpha, your abundances will will just be very large. Right here and here, you can see some bands where feasibility doesn't exist, right? This here, there's some negative species, and some other bands where there's feasibility, right? But there's not like a simple behavior in the sense that there's not one threshold beyond which you gain feasibility and you don't lose it again. There are several thresholds. And for the case of stability, this is actually not the same. For stability, the result is that when you pass some threshold, the alpha S threshold I was putting before, the system becomes stable and remains stable. But here we see a little bit of a different behavior. However, what we show is that when there is a value alpha F beyond which this behavior of becoming feasible and not becoming unfeasible again happens. So yes, you can have multiple bands, but there is one point beyond which you will always remain feasible. And that result is for any system without specifying the distribution, the random distribution of interactions. And what happens when now let's specify our distribution to a certain random ensemble rather to have like any system? Oh, sorry, and yeah, this is kind of the thing that I was telling you, right? That for stability, we have one value of intraspecific competition beyond which the system becomes globally stable. And for feasibility, we can have more, but there is one beyond which we will not change back. And but yeah, now we're gonna go from general systems. This was a result for general systems, but now we're gonna go to random systems. So now we're gonna commit to a distribution of the interactions that are sampled from random distributions, and we're gonna have this increasing the diagonal and see what happens. But now we do have the distribution, and in particular we're gonna have the same thing, but B is gonna be sampled from some distribution that could be normal, could be uniform, discrete. However, the statistics are some mean that is going to be positive, meaning these are competitive interactions. Some variance that we're going to set to 1 without loss of generality, because setting the variance of B to 1 and varying alpha is the same as keeping alpha constant and varying sigma. So we're just going to choose to vary the alpha. And the correlation between entries ij and ji is going to be rho. And the elements on the diagonal are going to be 0. So here we're going to have just the value alpha. And so when I mean that these systems are competitive, because one could ask, I mean, if this correlation is -1, you're going to have predator-prey interaction, so you're going to have positive on ones above the diagonal, negative below the diagonal. And so it's true, we can have negative interactions, but the sum over the rows need to be greater than 0. So that's why I say that this is dominantly competitive. And we're gonna ask, for example, now, what happens to that behavior that we were seeing where we have multiple intervals of feasibility when we commit to this distribution and we grow the number of species large. So here, that's what we're gonna plot. We increase n, and we fix alpha to some. Alpha is gonna be 0, and then what we do is increase alpha and count the number of intervals where I see feasibility, right? Because, for example, in the previous image there were 3, and now what I'm gonna do is increase n, count how many, and plot in the y-axis how many intervals I see. And for this random distribution, independent of the correlation, right? So all the I sample my entries randomly with correlation low, neutral, or high, and I always see that the number of intervals goes to 1. So there's a simple picture that emerges here when the interactions are random and the system is large, which is a picture that resembles the behavior of the stability threshold, right? Now, when we're in around 25 species, what we're going to see is the system is either unfeasible and then feasible, or feasible from the beginning and then it remains feasible. But there's only one transition rather than several. And this also happens for different distributions, right? If we sample from normal, uniform, discrete, all these distributions convert to just one interval. So that's nice, because now we have kind of this idea of 2 thresholds, a threshold for stability and a threshold for feasibility, and these 2 thresholds are unique, right? So we can calculate the probability of feasibility, right? And this probability of feasibility is just going to be, okay, now I have my system, I increase the alpha, and for each value of alpha, I sample many systems at that value, and I compute if my equilibrium is feasible or not. And then in the y-axis, I just plot the fraction, right, which represents the probability. If I sample 1,000 systems and 300 are feasible for that value of alpha, then my probability of feasibility is 0.3. And so we can plot this curve, right, which is telling you that for low alpha, the probability of feasibility is very, very small. And this is a result that is known already in the literature, because it's saying that when interactions are random and there's a lot of species, the probability to find a feasible equilibrium is 1/2 to the n. So that's this point here. But when alpha increases, there is this increase up to 1, and this increase is smooth. It's not, for example, like in the case of stability, you would have a very strong vertical increase to 1, kind of a step function when the number of species is large. But here we see a smooth increase rather than a step function type of increase. And sorry, this is for 1,000 species, right? These systems, these interactions are for 1,000 species. And these you can calculate for different correlations, and you can see that when the correlation is -1, so for predator-prey systems, it's easier to have feasible equilibrium than for purely competitive systems, and this is a result that mimics the results we have for stability, where predator-prey systems are more likely to also be stable. And so one thing that we can do here now is we have this curve for the probability of stability, and we can superimpose the curve for the probability of stability on this probability of feasibility curve. And when we do that, remember I told you that for large number of species, the stability curve is like a step function. So I'm just going to plot kind of the point in the x-axis where the system becomes stable. And those points are, sorry, before we get there, this is consistent, this is a universal pattern across different distributions. So when I sample my interactions from different distributions, I also see these same curves. And we have an analytic approximation for this that is valid for large number of species. Those are the white curves. And yeah, finally, when I plot these stability thresholds, right, these would be the points where my system becomes stable for that value of alpha. And so something to note here that is that to me is striking is that these triangles are always behind the points where the curves for feasibility start to increase. And that has consequences for dynamics, because before, in the plots I was showing before, I was telling you that the combination of feasibility and stability really determines what the dynamics are. And in this case, what we see is that if you increase alpha, when your system gains feasibility, which could be, for example, here, that system will always be stable because we've already crossed the stability threshold before, right? All these stability thresholds happen when the probability of feasibility is very, very low. So what we're going to see most of the times is that feasible systems are stable. Right? And if feasible systems are stable, I'm in the case where the dynamics are going to converge to stable equilibria. So I'm not going to observe chaos or limit cycles and things like that. Are there any questions so far? Good? Perfect. So in this sense, these curves of probability of feasibility now are the probability of coexistence, right? Because feasibility implies stability in this system. And this slide, which is very mathematical, is just to kind of give the key steps of how you derive these curves, these white curves here, the analytical curves. And I will go through it kind of quickly, just to not overwhelm. But yeah, basically what we do is we first make this equivalence that the y's are also representing the species abundance, but in a system that is a bit simpler than the system that we have with the x's. And what we see is that the feasibility on these two systems is if and only if. So it's if one system is feasible, the complicated system being feasible implies that the simple system is also feasible, right? So then we just study the feasibility on the y's, and for that problem, we can actually compute some statistics on the y's. And so for example, the expected value is 1 over alpha, the correlation is 1 over n, and the correlation being 1 over n means that for high n, this correlation is goes to 0, which means that the elements of y are going to be independently distributed approximately. And after some changes of variables, you can arrive to basically the distribution of y's. And what you impose is that all the elements of the vector are greater than 0. And the probability that all the elements of a vector are greater than 0 when these elements are normally distributed are just the cumulative distribution function of some standard normal with these parameters. And so this probability of feasibility is telling you that the system, the probability of feasibility actually only is going to depend on alpha and on the standard deviation of the y's. So this means that as long as the populations are statistically equivalent, you could have, for example, cycles like intransitive interactions, like the rock, paper, scissors type of interactions, or you could have higher order correlation. You only need to calculate the variance of the y's, and that allows you to estimate this probability of feasibility analytically. And so for our case, we were able to calculate this variance, and so that's why we're able to plug this thing inside and then plot the approximations for these curves, and that match very, very precisely. And
Can I ask you something?
yes.
So you are telling us that the probability of coexistence does not depend on the difference between the intraspecific competition and the average interspecific competition? It does only depend on the intraspecific competition, but not on how large intraspecific competition is compared to interspecific competition?
So
the average interspecific competition.
Yeah, no, it really depends on this difference. So that is true. But what I'm telling you is, yeah, that if you increase the intraspecific competition, then intraspecific competition is going to be much larger than interspecific competition. Is that so? Then you would have coexistence. Was that your question?
Is there any threshold beyond which you expect coexistence? For example, if I don't know, if the difference between the intraspecific competition and the average interspecific competition is whatever, you certainly will find coexistence.
Yes.
So is there a relationship saying that?
We don't have a relationship exactly saying what is the difference between one thing and another. I think you could probably calculate that difference. But what we're saying is that when alpha equals alpha f, so that's the threshold, right? A certain threshold, then you will have coexistence, for sure, guaranteed. And in this case, the average interspecific competition is a positive number. We are also saying that positive number doesn't matter. So you could have a model where the interspecific interactions has average 0, and that it would be the same feasibility properties as a model where the interspecific interactions has mean 5 for the same intraspecific competition. So in a way, the strength of competition doesn't really matter for feasibility. Yeah, so that's, exactly, that's point number 1. Sorry, I took a little bit of time to answer your question. I think now we're on the same page. So let's analyze a little bit slowly what this means for the dynamics of the system. And if you have this scale of alpha, right? This is just a one-dimensional scale of alpha, and you have 3 systems, A, B, and C. In this case, you can always, so you have these 3 systems with increasing intraspecific competition. And you have these thresholds for the system where, imagine at the beginning, right, you had your system with 0 intraspecific competition. You can always define these thresholds alpha S and alpha F, right? The threshold when you gain stability, the threshold when you gain feasibility. So depending on where is the system sitting, you're going to have one dynamics or other dynamics, right? So if you are in case A, where you are below both alpha S and below alpha F, that means that your equilibrium is not stable and not feasible. Right, which means you're going to have extinctions. As you can see, here the species pink goes extinct. And if you start your system from a different point, it goes to a different place. And that's because you also don't have stability. So you have multiple locally stable attractors. If now you increase alpha enough to surpass the threshold for stability, now the dynamics change a little bit, because you will still see extinctions, because you still are below this threshold where you have a feasible equilibrium, but starting the system from different places takes you to the same place, right? So you see the same species, green, going extinct. And then finally, if you pass both thresholds, then you see coexistence of all the species, because you are above alpha F, and because you're also above alpha S, you see stable coexistence, right? So everyone goes to the same spot. And this would be different in this if these two triangles were in reverse order, right? If you were in reverse order, you could see a feasible equilibrium that is not stable here in the middle, and that could lead to cycles, right? So we're saying here that these two things always happen in the same order with high probability, and that's why we cannot see cycles. And finally, I want to have an example of the dynamics, because so far what we've done is analyzing how increasing alpha leads to different dynamical phases, but alpha of a system doesn't really increase. Like your species compete with them with some strength, and that is like fixed. So that's what we're going to do here. Here we're going to have some ecosystem that is sitting at some value alpha here, where this is like how strongly the zebras compete with the zebras in your ecosystem. And then we're going to have we're going to run the dynamics forward. We're going to throw some species on this ecosystem, and we're going to run the dynamics forward, and we're going to see how this system evolves in time. And as this system goes in time on the x-axis, here also time, we're going to plot the thresholds alpha F and alpha S. Because remember that these thresholds are going to change depending on the number of species. These thresholds depend on how many species you have in your ecosystem. So if your ecosystem loses species through extinctions, you have to recalculate these thresholds and see what happens to them. This is what we see, right? So if we start our system, and then importantly at the beginning, the alpha is below both alpha S and alpha F, right? So then we're going to have extinctions. So extinctions start happening, right? Extinction, 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 extinction. And then as this happens, this alpha S and alpha F both go down. And then at some point there's this crossing where alpha S crosses the alpha of my system. And at that point, the phase changes to case B, right? So in the beginning, for case A, we would have this behavior. So if I start my system anywhere in a combination where species, in any combination of these species that are here that haven't gone extinct, then I'm going to observe this type of dynamics. Then once these species go extinct, the system has changed and is in a different dynamical phase. So if I take the species here, so I now discard all these ones that have gone extinct in phase A, and I start my ecosystem from any of these points from any point with this species present, that's what I'm going to see. Extinctions, but always the same species go extinct. And then in the end, more species go extinct here, and at some point alpha F crosses the boundary alpha of my system. And so this means that now my alpha is above the feasible threshold, so that means I have a feasible equilibrium, and because alpha S crossed before, that equilibrium will also be stable. So then in this phase, I see the stable coexistence of all the species that I was talking about. And this is for top-down assembly, but we can also look at this bottom-up assembly experiment where we're going to throw one species after another, right? And we can show that with high probability you can build this ecosystem one species by one without extinctions, right? And as you can see here, even when you build the ecosystem bottom-up, this alpha S is always below this alpha F. So that means that you're going to be always in the regime of feasible stable equilibrium, so I add another species and I'm still in that regime, so the invasions can proceed without extinctions. So this was the results, and basically just to like wrap it up, the conclusion is that, you know, in principle GLB models can exhibit any type of dynamics, as I showed before, and the dynamics are highly determined by this combination of feasibility and stability, right? But we see that in large models with competitive interactions, feasibility always occurs after stability in these models, and as a consequence, any feasible equilibrium will be stable, and we will only observe stable dynamics. And these are the conclusions. So thank you for listening.
Thank you very much, Pablo. And now it's time for questions. We have questions.
Thanks, Pablo, for the talk. I have a technical question, and then open the room for others. So when you were doing the bottom-up approach, you were showing that you are assembling the species from one after another, and they are becoming feasible and stable at the same time. How is this increasing the alpha that makes both the system be feasible and stable? Because as you are increasing the number of species in the community, the dominance of the diagonal should be stronger in order to accommodate more species to be in the system.
Exactly.
So how you do that exactly?
I think what you're asking is how do I calculate these things, right? Yeah. Because so these are the threshold for every species. Exactly, is going to increase because you have to accommodate more species, and as you can see, indeed, it increases. Sometimes it doesn't increase very much, or it even decreases a little bit, but overall it increases. And yeah, the way I do it is, I have originally my matrix of interactions, right, which is B, and then what I'm going to do is increase the alpha until when I solve this matrix of interactions, I have a positive equilibrium. So that's going to be my threshold. Yeah. Yeah. Yeah, and for the stability, I do the same thing, but evaluating a Lyapunov function and the eigenvalues of the matrix and stuff like that. Yeah.
Sorry, could you go a little bit more in deep to the bottom-up assembly, because I didn't catch exactly. Okay, thank you. Yes, so I was saying that could you please go a little bit more in deep in the bottom-up assembly processes, because when you said bottom-up assembly, I was imagining that you started with two species, and then you randomly added more species to the system. But I think it's not that what you are doing. So could you please repeat?
Yeah. So okay, these simulations I ran a long time ago, but I'm gonna try to remember what I did. I think what we did is, so sometimes you can add a species and have an extinction, right? Yeah, you could, particularly because these results that I'm showing here are only valid when n is large. So when n is small, you could have a case where these two things invert. And if they invert, you're going to have extinctions. But what I'm saying in this plot is that with high probability, you can find a path of assembly that will not have extinctions. But yeah, this is actually not backed by an analytical claim. This is something we observed.
Okay. And then I have another question, but okay. And if you could please return to the derivation.
Yeah. Oh.
Yeah. Okay. So.
I mean, this is not a derivation, but it's like the key steps of the derivation.
Okay. So
there's a lot in between.
So my first question was actually a little bit related with his. So.
Right.
The mu, that the mean interspecific interaction, there you suppose that is any positive number.
Exactly.
Okay.
And under that assumption, the feasibility doesn't change if I think it's 0.
Okay. But then if...
But it would change the relative abundance that you find at the equilibrium, right?
Yep, it will. it will. But it only changes by a constant of proportionality. So the sign will be unchanged. Exactly.
Okay. But then if you are in the limit of large n, so basically you are just having a system with very, very, very weak interactions, don't you?
I think, yes. I mean, yeah, this would be weak because we actually divide by n, by square root of n. So yeah, they would be weak. The larger n is, yeah.
Okay, and have you tried to see the dependence between the dimension of your system and you did, and this probability of coexistence? Yeah.
Yeah. What I haven't showed, so
those were not very large n's.
Yeah, they were 1,000. Oh, right. You mean the? Let me show one figure that actually it goes to what you're asking, but that I didn't show. Do I have Wi-Fi here? Yes, and I have it here. Perfect. So one figure to show is. Oh no, it's in the main. Sorry, my computer is very slow. Well, oh, there you go. No. Well, anyways, is that the alpha s is going to increase with n up to some asymptote, which it corresponds to the triangles. Wow, this is really slow. To these triangles here, right? Those are with n, it increases there and it doesn't move. But the alpha f is going to increase without bound. It doesn't stabilize at one value. So if you keep increasing the n on this curve, actually you will see these curves moving to the right, whereas these triangles wouldn't move. So this result is even more exaggerated, because those curves keep moving to the right as n increases. Yeah.
Thank you.
Thanks. So it seems that abundance is your response variable at all times, right, in these models?
Yeah.
So I can see interspecific competition affecting abundance. That makes a lot of sense.
Yeah.
But at the intraspecific level, competition creates asymmetric relationships, regardless keeping high abundances. So, for example, you know, in a forest, the trees reaching the canopy are the winners, and you can have a bunch of individuals as subordinates just waiting for a gap opening.
Right.
And in animals, you know, the reproductive success, for example, right? So a few males dominating, you know, and deciding which genes pass on to the next generations.
Totally.
But you are not considering the performance of populations, basically because this can have huge impact on the extinction probabilities beyond the competition. Right?
When you say performance, what do you mean?
Performance, I say, like size distributions, survival schedules, reproductive outputs, these kind of things. Because, you know, I see abundances, I see extinctions, but I don't know the reason of that extinction.
Right.
So what do you make of this? I mean, abundances perhaps is the simplest way to look at it, but how populations perform regardless the abundance, that's in my opinion, you know, a step closer to reality.
Right. No, I agree.
What do you think about that?
So I definitely agree with you that this model is very bare bone, stripped down model where we only have interactions that are not even representing some, like, for example, resource consumption or spatial differences or reproductive dominance, like you were saying. I think including those things is always possible. They complicate the math incredibly.
Well, that's the job.
Right. Yeah, that's the job. Yeah. Yes. But so it's really hard to have some analytical kind of general statements about these systems, and I think sacrificing kind of like reality to gain generality is one decision, right? It's a lot of like what physicists do is kind of this thing. They try to find these general statements. I think if it is a fair criticism that this model is not capturing like very real questions that happen, for example, in microbial ecosystems, in questions of like how, for example, how many resources you put in, can you predict based on the resources you put in how many species are going to coexist? None of that is captured here. I don't have space. I don't have space time dependence on the interactions. So I think these results are maybe to be taken as a somewhat of like a null expectation of what is the generic behavior I should expect in the absence of these ecological forces that could change this thing, right? And I'm not saying there's no cycles in nature, of course. I'm not saying there's no chaos in nature. I'm saying if these are the assumptions, which obviously ecosystems are not random and they're not fully dominantly competitive, then this is what we should expect. And departures from this then would inform us that there are some ecological forces we're not thinking about that we should think about. And a clear example of a model where departing from this that is actually very close to this model is a Lotka Volterra model with an immigration term. So you basically put an immigration term outside of this equation. Outside here you put a plus some small quantity that is kind of modeling constant invasion of species. And for example, this is a good model of like a patch of some plot where even if a species go extinct in the plot, you can have invasion from other parts of the plot, and then the species eventually resuscitates. And so if you're trying to model patches of land, then this is not the good model to think of, right? So these are all like modeling choices and assumptions that one is making, and as long as you think your system is respecting the assumptions, then at least we have that expectation for that case, right?
But these changes in abundance, it's a general pattern, but changes in survival and reproductive schedules are so general as well. That's it's a target for modeling actually.
For sure, I agree with you.
So imagine that instead of abundance, you are modeling survivorship or reproductive output, and then from there, you can build up on abundance, on the final abundance, and how the populations look like, and these kind of things, So basically, because when I saw the figure with the giraffe and the zebras, those relationships are totally different.
Right.
Totally different.
Probably. Yeah.
So both species can have super nice and healthy populations, right? But the structure within these species populations can be quite different.
Yeah. I mean, I agree. And thank you for these comments. I think if I had to give an opinion for why there's this like huge focus with Lotka Volterra and abundances for the past half century, it's because of May. Robert May kind of ignited this agenda of this question of like, ecosystems shouldn't be stable, then why do we see stability? And it's been a very elegant way to do mathematical modeling ecology. But honestly, my opinion is that the reason why that's happening is because like it's a good excuse to do progress. It's an elegant framework, but it's not because theorists are trying to understand the world because they're concerned with the world. And I think there's a lot of room for that. There's a lot of room for theory to go to the real, like put the boots on, go out and see, or go to the lab and be like, okay, what are the questions that you guys don't know the answer to? Let's try to really work hand in hand to answer these questions. So in that sense, I agree with you then. Thank you.
So my question perhaps is a bit fussy, but let me help you. You can help me.
We can build it together.
Yeah. Okay, great. So when you were saying that with one species you only have a steady state equilibrium, but with two species you can have another thing. With three species you can have cycles, and with four you can have chaos. But then you went to a large N that you might have like hundreds of species over there.
Yeah.
Have you explored in your work the N number in which you change from chaos to stable equilibrium? So you're making the jump from 4 to 200. But what happened in this range of these two order of magnitudes? So do you know at which number of species you change from chaos to stable equilibrium? So which is the threshold of N that you change the dynamic of the system?
That's a really good question. That's my chapter 3 of my thesis. So stay tuned. But yeah, I mean, it's yeah, I don't really know, and I think it also depends on the structure of the interactions, which we haven't considered here, by the way. And but it's very hard to look at this type of questions of what are the type of dynamics if your type of dynamics are not stable. You're looking at coexistence through chaos, coexistence through cycles. It's really hard because the conditions you have to impose are some conditions that are called permanence, which basically means that maybe you don't have a stable attractor, but your boundaries are repelling, right? So you, in this sense, you have a permanent coexistence state. The mathematical conditions for these are super hard to implement in the computer, and they escalate, of course, as 2 to the n. So we have some results that we're trying to run a little more, but yeah, I think my intuition is that it's gonna depend more on the structure than on N, the type of dynamics. And for this one, I think you can already have a stable equilibrium with 4 species, but it's really and actually chaos is very hard to find in these systems. But this plot, what I was saying is that you can find it for 4, and you can also find it for infinite number of species. It's just increasingly hard, and but there's not, I think, a clear threshold. It will be more of like a diffusion, kind of like, okay, it's less and less likely to find it until it's very, very small, the probability.
Okay, but let me continue on that because I think it's very interesting. So if I have 4 species, I can reproduce a stable equilibrium, alternative stable states, limit cycles, and chaos with 4 species because I have many degrees of freedom of how to parameterize the matrix of species interactions by which I can have each of these results independently. And actually, if you take my paper of 75, I can obtain any kind of dynamics with 3 species, including cycles, stable states, and so on. But as soon as I increment the number of species in the community, there are some parameterizations that are more likely to occur in nature than others. So we know from many literature that intra in general are stronger than inters. That is a common result both for plants and animals. But if I want to produce chaos in 200 number of species, just by interactions, it means a highly unlikely matrix of species interaction to occur. Just because the combination for that to happen, how you parameterize that, is compared to all the number of parameterizations that we can have, is very, very unlikely.
Yep.
It might be 1 or 2 out of millions of them.
Right.
So it's not a correlation in how you can maintain feasibility and stability with the number of species in such a way that you constrain the likelihood of the matrix, and therefore you reduce the dynamics that you observe in the system. Is perhaps I explain myself clear, or?
Can you repeat the last sentence?
Yes. So because obtaining different kinds of dynamics when you have a large N is very difficult, because some matrices are going to be very, very rare to be found compared to the amount of they are. It's not the N imposing a restriction in the dynamics that you are observing.
Yeah. I don't think it's necessarily a matter of sheer number of species. I think there might be configurations for which cycles are unlikely, even at large numbers.
Okay.
And I think it could depend. We were talking about Hopf bifurcations before. I think it depends on the eigen spectrum of your random matrix. So if this spectrum is, for example, a ball with one eigenvalue on the real axis, then it's going to be very hard to see cycles, because once you cross this real value, you're done. But if you have imaginary values, and you have the bulk here, these imaginary values, when you cross them, then that's going to induce cycles. So I think there are some structures, and that's exactly what I want to look at, that will generate chaos at high probability.
Okay.
Or limit cycles.
Yeah, thank you.
Okay.
Previous question. So, if all interspecific interactions are positive, the only condition for a system to be feasible and stable is the intraspecific competition.
Correct. That's the statement.
And the larger the positive average interspecific interactions, the larger the intraspecific competition must be in order for the system to be stable and feasible?
In order for the system to be feasible, that only depends on intraspecific competition. That doesn't depend on interspecific competition.
Feasibility.
Yeah.
And for stability?
For stability, I don't have like a mathematical result off the top of my head, so I couldn't make a statement on that like right now. But our results are showing, I think not, because I mean our results are calculated without doing this subtraction for stability, and we do observe that they're always in the same order. But I would like to go back to the notes and see exactly where is this said. So I don't want to say no or yes without knowing exactly, yeah. Okay. But in simulations, that's what we see.
Yeah, because I guess if interspecific competition is quite high, a positive value,
Mm-hmm.
for the system to be stable, there must be a lot of intraspecific competition. Yeah, that's my guess, right?
So,
Yeah, okay.
Yes.
Oh, okay. Okay, so I thought, yeah, for that, we don't, this could be true. We are not looking at those systems. Yeah. I mean, I think that's actually true, because you have to look at the eigenvalues of the matrix. So.
but I would say that the more facilitation, the more stability in the system, and not so much the minus an alternative mechanism for interspecific competition for determining stability. The other thing is that there might be predictions about what is the kernel about the subjectivity that does not make any sense, because they are superior subjectivity or things like that. So you need additional mechanisms to understand a bit whether the equilibrium that you are obtaining makes sense or not.
Yeah, in mutualism systems, you can have unbounded growth pretty easily. So that's something that is hard to deal with.
But there are other types of matrices like Volterra, the ecological stable matrices that can be interspecifically facilitative and do not have unbounded growth. So this is a possibility.
Mm-hmm.
You have to take into account the structure of this.
Mm-hmm. Mm-hmm.
Well, okay, so we can continue the discussion during lunch, but we can call it a day. And thanks Pablo again for his talk.
Thank you, guys.
And see you next seminar.
Thank you.